Hey, mathletes, what we're going to look at in this video is the limits of logarithmic functions. Now, in your last class, maybe you didn't love logarithms when you were doing logarithms, but they take on a different feel in calculus, so don't worry about that, okay? Just remember, you do have your laws of logs, and so your laws of logs tell you different ways to simplify and expand things. And we will come back and we will need specifically the one I just wrote out for the expansion of the product of M&M there inside the logarithm. But, you know, these were your major log laws when you were working through this, when you first learned them, right? And so it's not a bad thing to remember them a little bit, okay? But there they were. We'll come back and revisit this log law closer to the end of the unit, all right? But until then, what we want to do here is we're just going to look at the limits of logarithms. So the same as the limits of exponentials, or any limit for that matter, it's a heck of a lot better if we've got a picture. So for a logarithm, again, the first thing I'm going to do is I'm going to draw an exponential. So it says a is greater than 1. So I'm going to draw an exponential with a is bigger than 1. So I know my y-intercept is at 1. I've got a horizontal asymptote, and there it is. There is y is equal to a to the x. The reason why I'm drawing that is because if I know the graph of a logarithm, if I know the graph of an exponential, I know the graph of a logarithm. Because they're inverses of each other, which means they're undoing each other, which means we're switching x and y. So the y-intercept goes from +1 to an x-intercept at +1. So we switch x and y. Our horizontal asymptote will become our vertical asymptote, and there is roughly our log graph right there. Okay, and so when you're doing these, sometimes teachers talk about it as a diagonal reflection because it's being diagonally reflected around the line y is equal to x. Okay, so it's nice. The reason I want to do that is because that way, if I know one function, I know both. Okay, that's just the one thing I like to think about here. So the domain of your log graph is 0 to infinity. The range is all real numbers, so -infinity to infinity. You do not have a horizontal asymptote, not applicable, but we've got a vertical asymptote right on the y-axis there. That's x is equal to 0. Okay, so there's your graph of a logarithm. Now, I've got another one here. What we're going to look at here is something really, really, really important that's going to start appearing more in this unit. It's this. Y is equal to log base e of x. Now, in the previous videos, I've talked a little bit about E. E is Euler's number. It's a very, very, very important thing. I just need you to know again is that E is approximately 2.718281828459045. It keeps going. Okay, it's irrational. But E is so special that when we write it as log base e to the x, we actually rewrite it with its own name. We call it lnx. So this is a logarithmic naturel, a natural logarithm. Some people will pronounce that ln x. Okay, so it's a natural log, and it's on your calculator, probably right above your log button somewhere. Okay, I don't need you to know much more about it for now, but I just need you to know, guess what? Since a is bigger than 0, the base is bigger than 0, guess what? It follows the exact same shape as a normal logarithm. Again, we're going to want to work with this because E makes our life really easy when we're taking derivatives. It's great for continuous growth. Okay, so for now, that's what I need you to know. Again, the domain and the range and everything else will stay the same. So there's nothing too different about this. I just want to expose you to the idea of what that graph looks like. We'll talk about that more when we're doing some differentiation coming up. Okay, let's do some limits. Now that we know what the graphs look like, let's do some limits. Now, my very first one, I've got e to the x. So I'm trying to get this in here so that you remember what this looks like. So e to the x. So e, I just told you, Euler's number is 2.718281828459045, yada, yada, yada. Okay, so as an exponential, the base is bigger than 1, so it's increasing. Okay, so that's what the graph of e to the x looks like. So 0 from the right. Well, the limit is 0 comes from the right. Well, remember, our y-intercept is always originally at 1. That's it. Okay, so just as a review as to what e to the x looks like. So now the next one says natural log x. Okay, no problem. What he just told me is a natural log is pretty much the same thing as a logarithm. It is the same thing. It just has a special base. So it's just going to look like this. There it is. So as x goes to infinity, the y values grow without bound. So the y values are getting bigger. So we could say positive infinity, and really the answer is does not exist, but that positive infinity is there for the sense of direction. Just like that, friends. So don't panic when you start seeing ln, natural log. It's just a logarithm, okay? And the rules of them in terms of transformations are the same as any other logarithmic graph you've dealt with. So number 3 here and number 4 says the natural log of x minus 4. So what that means is this graph has been translated 4 units to the right. So now instead of my x-intercept being at 1, when I draw this thing, my x-intercept is now going to be at 5. Okay, so there's that. And so then I say to myself again, the limit as x goes to infinity. Well, the limit as x goes to infinity of this one grows without bound. That would be positive infinity, or does not exist. Easy. Okay, as soon as you got the graph done, these are easy questions, right? Okay, the next one, the limit as x approaches 4 from the right. Okay, I'm going to fix up my graph there just slightly because I want to draw in just one more thing here, friends. There's that, but I just want to squeak in then, if we shifted this graph 4 to the right, if we horizontally translated it, so also did our vertical asymptote at x is equal to 4. So as we approach 4 from the right, now it's easy to see that this graph is moving downwards without bound. It's going to negative infinity. Again, we could say that this does not exist. So friends, natural logs are nothing to be afraid of. They are something new, but I could have taken these questions and instead of writing logarithm, natural logarithm, I could have written logarithm. And our answers would have been the exact same. The thing is here is we want to be exposed to what a natural logarithm is and E, Euler's constant or Euler's number, because it's going to help us out so much coming up and the applications are very robust. So there it is, friends. Logarithmic limits, always draw a picture and then go from there.